Okay, so let's get started. Today we will continue our journey through the physical layer and talk about signal constellations, and then a little bit of the final touches on the pulse amplitude modulator receiver. And then we will switch over and do a quick review of some basic concepts in probability and so forth. And these are things that we need in order to compute error probabilities, which will be the topic of tomorrow's lecture. Okay, so remember that we have talked about pulse amplitude modulation, which is the workhorse for digital communications, I would say. And then we have talked about receiver structure of this sort, where you have a receiver filter which is sampled once every t seconds. And t here is the same time, is the time between consecutive pulses here. So we sample this at symbol rate, and then we get some output y-ok. And then the question is how to process y-ok later on, and we will see momentarily how to do that. The first thing we would like to do, however, is to make sure that if we forget about the noise, then clearly we would like yk to be equal to ak. Okay, that seems to be a reasonable design criterion. And if one just simply looks at what the output from a generic filter with impulse response f is, when the receiver transmit pulse is g, then one can just simply compute it like this. And we see that y-ok here consists of many terms. One term, which is the desired term, which is ak, multiplied with some constant. The value of the constant is not so crucial. We can always compensate for that later on by dividing with it. But anyways, we would like to have ak here. Of course, the constant cannot be 0, but let's assume that that is not the case. And then we get a sum of many other terms of similar nature. It's amplitudes, symbols, multiplied with samples of a function. And this function h is the convolution of the transmit pulse and receive pulse. And what we would like to do is to make sure that in the noiseless case, we would like this to disappear. Okay, that would be good. And how to do that is to, of course, one way to do that is to make sure that all the samples here are 0. So let's impose that condition. So this is the time domain condition on intersymbol interference-free transmission. And this is the frequency domain condition. So whether one wants to check if one's h is good, then one can either look in the time domain or in the frequency domain. Which one is the most convenient one can pick, right? Just as we normally do, we have the frequency domain, we have the time domain, and we can solve problems in both domains. Sometimes it's easier to be in one than in the other. Okay, so then of course we would choose the easy way out because we are basically lazy people, right? Okay. So from this criterion, we can see that if we impose that g has to have a certain bandwidth w, then we can say something about when intersymbol interference-free transmission is possible or not. And remember, that has to do with the transmitted pulse, it has to do with the receiver receiver filter impulse response, and with t, capital T. And the reciprocal of t, 1 over t, is the symbol rate, rs. Okay, so if the symbol rate is greater than twice the bandwidth, there is no way we can have intersymbol interference-free transmission. If it's equal, then it's possible, but only if g and f, when we convolve them, it happens to be exactly this sinc function. If the symbol rate is a little bit less than twice the bandwidth, then it's possible to do this, and then there are many choices for g and f for which this is possible. Okay. And one such, if we convolve these and we get h, and then we take the Fourier transform of that, one such choice in this case is to select the Fourier transform of h to be a raised cosine spectrum. Okay, and the raised cosine spectrum looks something like this. You know, it's basically a flat line and then a cosine that takes it down to 0 when we plot that. And the bandwidth of this, the bandwidth of the raised cosine pulse here is given by this number. It's 1 plus alpha divided by 2t. And maybe we should write here that this is true when alpha is between 0. This is defined, the raised cosine pulse is defined for these alphas only. Okay, so if we put alpha equal to 0, we have 1 over 2t, which is the fastest, which is the least bandwidth we require for intersymbol interference-free transmission, according to this criteria. And we see then that, or it's not obvious from the frequency domain here, but then it reverts to a sync pulse. Okay, but in general, we put some alpha here, a little bit more than 1, a little bit more than 0, and then we extend the bandwidth of the transmitted pulse in order to make the implementation of the receiver and transmitter easier. Okay, so you just have to take my word for that that is the case. Okay, so for the total bandwidth for raised cosine pulses, W, is this 1 plus alpha over 2t, just as we saw on the previous slide. So it's 1 over 2t, which is the minimum bandwidth which is required. And then there is some extra bandwidth, and this is sometimes called excess bandwidth. And of course, we want this to make this as small as possible, but still maintain nice properties of the transmitter and receiver. Okay, so now we know how to form the convolution between G and F. We would like that to have a Fourier transform which is a raised cosine pulse if we want to be band limited. Okay, but how should we pick G and F? There is some freedom in this. And the best way to do this is actually to make the receiver filter matched to G. We will see later on why this is a very good choice. So essentially what we would like to do, or what we want to do, is to make the receiver filter impulse response to be matched to G. Okay? That does not mean that F should be equal to G. No, not at all. It should be the complex conjugate of G. It doesn't matter when G is real valued, of course, but then it should be the time reversed version of it. Okay? So the impulse response is the time reversed version of G and then complex conjugate. All right, so if we have a matched filter and we have some input. Okay, so here we have a matched filter and it's matched to the pulse G. And if we have some input R, we get an output Y, which is the convolution, of course, between R and the impulse response. And if we sample that at time 0, we get a number. Let's call that Y. And that number is the amplitude of the output filter at time 0, by definition. And that, one can show, is the inner product between the input, R, and the pulse to which this filter is matched. Okay? So again, it's not the inner product of the input and the impulse response, but rather to the pulse to which the impulse response is matched. Okay? And this is a very useful formula later on. And in particular, if we say that the input to the filter here is some scaled version of the pulse to which the filter is matched, then it's easy to show that, just putting, instead of R, we put A times GT here, like this. And then one can break out A from this due to linearity of the inner product. And the inner product of G with itself is just the energy of G. So then the output Y here is the amplitude multiplied with the energy of G, which is a positive number. So you can sort of think of this as maybe A here is some information. It's the symbol that we transmit at time 0. So this will be the data that we transmit. And then the sample of the output of the matched filter is simply a scaled version of the amplitude that we transmitted. Okay. So that's actually what's going on, as we will see a little bit later. Okay. But still, it begs the question, how should we then choose G here in order to get intersymbol interference-free transmission? Well, then we know that G times the impulse response of the receiver filter should be a Nyquist pulse. And one way to do that is to choose G as a root raised cosine pulse. So root raised cosine pulses are pulses whose Fourier transform is the square root of a raised cosine pulse. Okay, raised cosine pulse Fourier transform here. Take the square root of that, we get a root raised cosine pulse here, or the frequency response of it. Okay, in the time domain, one can inverse transform this and we get this. Okay, so yeah, it's just what it is, right? So choose your alpha and then we can implement this. Okay, and again, this is true for 0, alpha greater than 0 and less than 1, like this. Okay, so it's pretty clear now that if we take G, okay, and we see that G here, since H is a real valued function, the square root of that is also a real valued function. So typically Fourier transform are complex valued, but in this case it happens to be real valued. So G is real valued. So if we take G and multiply it with itself, then we get the spectrum of the raised cosine pulse. If we inverse transform the left-hand side and right-hand side, we get the convolution of GRRC with itself, and that becomes then the raised cosine pulse. Now, the beauty of this is that this one is actually symmetrical in T. So what I would like to say is that the root raised cosine pulse, if I time reverse that, I simply get the root raised cosine pulse again itself. So if I want to have a matched filter to the root raised cosine pulse, I need to time reverse it, but then I get it back, right? So there is no need to time reverse it in this case. That's a very special case, only holds when pulses are symmetrical around T, something like this, right? Then this will work. Time reverse doesn't, flipping it doesn't do anything. Okay, but that's a special case. Now the second thing that, so that's about root raised cosine pulses and root raised cosine pulses. Now let's look at the spectral efficiency. Okay, so what is that? Well, it's some number that tells us how good we are at using the bandwidth of the channel. So if the bandwidth of the channel is W, then we need to transmit the signal whose bandwidth is less than W. And suppose we transmit RB bits per second, then the spectral efficiency is just the ratio between the number of bits per second that we transmit and the bandwidth. Okay, so the unit of the spectral efficiency is bits per second per hertz. Actually, it's unitless. So if you, it doesn't have a unit. It's the ratio between two things with the same unit. But if we want to be explicit what this really means, bits per second per hertz is a good thing. Okay. Now, if we use M-ary PAM with the root raised cosine pulse shape, then the spectral efficiency is twice the log 2 of m divided by 1 plus alpha. So if we want to have good spectral efficiency, high spectral efficiency, there are two things we can do. We can reduce alpha, or we can increase m. These are the two things we can do. Okay. Now, alpha cannot be less than 0, so that's the smallest we can make it. For implementation reasons, we want to have alpha a little bit higher than 0, maybe 0.2 or something like that, or it could be even higher if we want to have a simpler implementation. But then also we can increase the spectral efficiency by changing m. And we will see later on that that actually requires more transmit power. Okay, we don't know that yet, but that would prove to be the case. Okay, now the last thing we did last week was to look at the complete receiver for pulse amplitude modulation. So first of all, there is a change in notation. Transmitted pulse now is no longer G, but H. And I'm sorry for that, but that's just to be consistent with the book. So from now on, we would think of the transmitted pulse to be H. Okay? And then we say that the receiver filter should be matched to what we transmit. Okay, so it should be H conjugate negative T. That's the receiver filter impulse response. Okay, and then we get an output Y. We sample that once every T seconds, and then we get YK, as we did before. What we do then is the following. We take we take yk, and then we multiply with the inverse of the energy of h, and then we get z, and then we feed it through the slicer that I will explain momentarily what that is. But it's essentially a decision device that looks at this number and then outputs a decision or a guess on what AK is. And remember that AK is a member of the symbol alphabet. Okay, so it's some set of possible amplitudes. In general, it's like a capital A1 and then up to capital AM. Sorry for the mess here. But anyway, so the amplitude here is in some set. Okay, and this set is the input to the slicer, and the output is a member of this set. Essentially, or what the output is, A hat K, is this member in this set which is closest to CK. We will see that later on. Okay, so CK here is YK divided by the energy of H. Okay, that's what this thing does when it goes through this device. This is multiplication with whatever is here. Okay, so that's just to explain the block diagram. Now, the slicer output is therefore the element in the symbol alphabet alpha, curly A, that's closest to the input. That's what it does. And this turns out then to be a minimum distance receiver. Okay, so this part to the right here is a minimum distance receiver if the following condition holds. That is that there is no intersymbol interference in this scheme. So how do we check for intersymbol interference? Well, we take the transmitted pulse, we convolve that with the receiver filter impulse response, which is now matched to H. And then we know from previously that for K equals 0, this is equal to the energy of H. That's true for any pulse. Okay. However, to make this a Nyquist pulse, all other samples needs to be 0. Okay, so this is a condition that we impose. And this is true, for instance, if this is a root raised cosine pulse. Okay, there are other choices also. Okay, questions before we continue? No? Okay, so let's look a little bit on this slicer thing. So what is the slicer? Slicer. Okay, so the slicer is a device. So a block diagram of it would look something like this, which has an input, let's call it Y, and it has an output, let's call it A hat. Okay, and the output is the element in curly A which is closest to Y. Okay. So we look at the input and we look at all possible elements in A, and we spit out the element in curly A which is closest to the input. So in mathematical terms, A hat is the arg min of the distance between Y and A, where A is some element in curly A. Okay. So I hope we're starting to get more and more comfortable with this type of notations. What are we looking at? What we are looking at this, which is the distance between Y and some A. Okay, so this is the distance between Y and A. And what is A? Well, we check all A in the set curly A, and then we look for the minimum of this. Okay, and we're not interested in the minimum value per se, but we are interested in the element A, which minimizes this. So the arg min picks the A, which minimizes this. Okay? And that is A hat. Questions? Okay. Small example. So suppose curly A is a set of 4 values, -3, -1, 1, and 3. Okay. So what we want to do then is to, for each possible input, okay, so actually the input should be, this is all true, but let's pick the input Z instead, and put Z here instead. Doesn't matter, right? Okay. Just to be consistent with what's on the slide. Okay. So what we want to do then is to, for every Z, assign an A hat. Okay. So if we draw a line here, so we know that Z, the input, could be any number, right? And for each of these numbers, we need to figure out what A hat is. Okay. So the simpler thing to do, or one simple thing to do, is to take each possible amplitude and plot it on, we take each element of A hat and plot that on the Z axis here. So the first element here is -3. Second element is -1. Third element is 1, and the last element is 3. Okay. When we do that, we call these constellation points. Or the set of these points is called the constellation. So think of this as if you look at the sky and there is no clouds, you see stars in the night, okay? So constellations, okay? So like that. Okay, and then what we want to do then is to figure out for each possible Z, which output should we assign to the slicer? Well, one way to do that is to find the middle point between these constellations. So the middle point between 1 and 3 is what? Well, it's 2. And the middle point between -1 and 1 is 0. And the middle point between -3 and -1 is -2. Okay. And once we have done that, we know that for all points on the Z-axis, which is to the right of this boundary, we are closer to 3 than to any other point. Right? So for each point on the Z-axis here, we're closer to 3 than to any other point. So in this part, we know that A hat should be equal to what? What should A hat be? 3, exactly. Good. So then we know what's going to happen to all points which are on this part. I mean, it extends out to infinity, or in your way, it's like to infinity that way. Okay. So we continue. All points which are between 0 and 2, what should they be mapped to? 1, exactly. And because, of course, all points on the Z-axis in this interval here is closer to 1 than to any other signal constellation point. Okay, and you see the pattern here now. So all the points in between here should be mapped to -1, and all points here should be mapped to -3. Okay. So by doing this, we have specified for each possible Z what the output should be. So this is a complete specification of the slicer. Or, if you like, it's a solution to this formula here for each value of z. Okay. So this geometrical constellation, except for explaining how things are related, is actually quite useful later on when we want to figure out the error probability and so forth. So these regions, for instance, the region here, all the points on the z-axis which are mapped to all points on the z-axis which are mapped to a specific decision, that's called the decision region for that constellation point. So this part here is the decision region for a specific output of the slicer, or decision or guess on what the transmitted signal is. So this is for the decision region for when A is equal to A4, which is -3 in this case. So this is equal to A4. And this is equal to A1. Okay, if we just enumerate them like this. Okay, so we see here that we have one decision region.
A question there.
Yes?
Isn't it A1?
Yeah, it would be if it was -3 here, but which is not the case, right? We see that the output here is 3, so like that. Sorry. Right? So the output here is A hat equals 3, so this is the decision region for A equals 3. Okay, and then we have a decision region here, and one here, and one here. In general, we have one decision region per possible amplitude or symbol in the symbol alphabet. Questions? No. Yes?
This decision region then set bigger than 2 or bigger than and equal to 2?
Ah, that's an excellent question. So if I rephrase the question is, what's going to happen on exactly the boundary here? Okay, I have neglected that. And the reason for this is that it doesn't matter actually. We should, on the boundary, you should pick either this one or this one because they're on equal distance. So it doesn't matter. Okay, for completeness, of course, we need to specify which one we go for. So we can go for, say, the lowest index. So on the boundary here, we go for this to the left. Or we can decide to go to the right, as long as we decide something. Okay. So for completeness, we might want to say that we go to the point to the left. Okay. So then the boundary here belongs to 1. The boundary here belongs to -1. The boundary here belongs to -3. As we will see tomorrow when we compute error probability, the error probability does not matter at all on this decision whether we go this way or that way. It would turn out to be not important. But for real implementation, we need to decide something, of course. Okay, thanks. That was an excellent question. Anything else? Okay. So what we have done now is that we have explained this device here. So the output here is the closest point in curly A to the input. And in the noise-free case, and if this is true, then y of k is equal to A of k times the energy of h. We know that from the properties of the matched filter. And then we know that zk, which is yk divided by eh, is then equal to ak. And therefore, the output, which is the closest point in the symbol alphabet to ak, is also ak. So everything is perfect. Okay. So in the noise-free case, everything works perfectly. It turns out that in the noisy case, this is also the minimum distance receiver, which we will see tomorrow is the best receiver we can hope for. Okay, so this is a good thing. Okay, now to say something about that things are the best we can do, we need to first of all, we need to decide what is the best. And we will do the following. We will model, well, it's like this, that most unfortunately, how do I get rid of this? Most unfortunately, we have noise, okay? We have noise. Okay, and the question is, how are we going to model the noise here? Well, the noise sort of per definition is unpredictable. It's something that we cannot really measure and compensate for at the receiver. It's something that's completely unpredictable. So we model this as a random quantity, actually as a random process. And therefore, sometimes the noise is nice to us and sometimes the noise is bad to us. So sometimes we will make an error here. That is that the output is not equal to AK, it's something else. And then we have made what's called a symbol error. And what we would like to do is to design a receiver such that we minimizes the probability of making an error. Okay? Or in other ways, to maximize the probability that we do the right thing, a correct decision. So what we want to do then is to figure out what is the probability that we make a right decision, or equivalently, what is the probability that we make a wrong decision. And to do that, of course, we need to invoke theory about random things, so probability and so forth. So we'll make a little bit of a detour now for a while to explain some basic concepts in probability and expectations and so forth. And these are things that are actually prerequisites to the course, so I won't teach them properly here or explain them properly here, but just to sort of refresh your mind about this and also to set some notation. If you think this is strange, complicated, or you don't remember this, there is an excellent online course for refreshing your skills in this. The link is on Ping Pong, and also you can always come and ask, of course. But I actually will assume that you know this pretty well already. Okay, so and also if I would say something about probability and random variables and so forth, this is something which is typically thought of as being complicated when you first exposed to it. It's strange things happen here. But I would say it is really the fundamental thing for all human knowledge, right? Without this, we would still be wandering around and doing bad things, right? So if you have a good grip on this, randomness in general, random processes, random variables and so forth, it's super useful, right? So don't give up on this if you think it's strange or difficult. I mean, try to learn this, and it will pay big dividends in the future. Okay, so that with that little speech, let's go on. Random variables, these are things which are unpredictable. So before observing the value of a random variable, I don't know so much about it. I know the probability that it can take on certain events, but that's it. Okay, so the cumulative distribution function, or CDF, and the probability mass function for a discrete random variable, they are defined as follows. So this is the CDF, and this is the probability mass function, or PMF. So if we start with the PMF, it's the simplest things. Okay, so it's the F here, small f, for probability mass function, capital X to indicate which random variable we're talking about, and then some dummy variable U. You can pick any value, anything you like here, except capital X, I guess, which would be strange. But anyways, so it's a function of u. And what is the value of that function? Well, it's the probability that x takes on this value u. Okay, so it's a basic probability. So if I had flipping a coin, it could be tails or heads. If it's a fair coin, then there is a probability 1/2 it's tails, and probability 1/2 it's heads. If I have a die and toss it, and all 6 sides are equally likely to turn up, then the probability that the die is 1, 2, 3, 4, 5, or 6 are all equal to 1/6, right? But these are, of course, special cases. Then the CDF is the probability that the random variable is less than u. Okay, so it's probability that x is less or equal to u, Okay. The CDF and probability density function for a continuous random variable are defined as follows. Forget about that. I updated the slides just before going to the lecture, and this is the price you pay for that. There will be some errors. Okay, but the CDF here, we see it looks very similar to the CDF of a discrete random variable. It's simply the probability that x is less than the value u. If I want to find a probability density function for a continuous random variable, I cannot do this, because the probability that a continuous random variable takes on a specific value is always 0. At least for the continuous random variables that we will look at in this course. Okay, so the probability that the temperature in this room is exactly 22 degrees is 0. Right? But we can assign a probability that it's between 18 and 23 degrees. This is possible. So we can assign probabilities for intervals on continuous random variables, but not for single values. Okay. So in the continuous case, we have still small f of x, which is now a probability density function, and it's a function of u, and it is defined as the derivative of the CDF. Okay. So if we have the CDF and we take the derivative with respect to the variable u, we get a function, and that function we call the probability density function. All right, so the purpose of this, or one purpose, is that we can compute probabilities using the CDFs or PDFs, and which one you choose depends on which one is the most convenient, of course. Okay, but anyways, if we have a probability of this nature that we would like to know when x is less or equal to b and greater than a, it's in a certain interval. By definition, we can write this as the probability that x is less than b minus the probability that x is less or equal to a. Okay, then it falls into this interval here. And then by just plugging in the definitions of the CDF, we get a CDF expression like this. So we take the CDF at b and subtract off the CDF at a, when b is the upper limit of the interval and a is the lower limit of the interval. And if x is continuous, then we can find that by integration of the PDF from a to b. And if x is discrete, we find that by just summing the values between a and b of the PMF. Okay. So, questions? Comments? Is this too slow? Too fast? Just right. Okay. I'm glad. Okay. All right. So, expectations. This tells us something about the average value of random events. The expected value, or in Swedish, väntevärde. In English, it's also known as the mean or sometimes the average of a random variable, is defined as follows. Okay, so E here is now an operator. It has nothing to do with energy or something like this. It's just an operator telling us that we are interested in the average value of the randomness which is inside the brackets here. So if the randomness is just a random variable, it's the average value of this. And it's defined as the integration from minus infinity to infinity u fx u du. Okay. If you don't like u, you can put in any other symbol you like, but I would avoid using capital X, because then capital X has a specific meaning here, right? Very often you see instead of u here, small x. Okay? So once we have defined this, this basically tells us, the basic idea about this is that the expected value is the expected value, right? So if you observe the random variables many, many times, you expect on the average to see the expected value. It would deviate from the expected value, but if you take the average over all your observations, typically it becomes the expected value. That's at least what we expect it to be. Okay, right. So if we have a function, if x is something which is random, and then we take a function of this, maybe the cosine of it, or the square of it, or some function of it, we still have something which is random. So a function of a random variable is a random variable. And then we can find its PDF or CDF and so forth. But that's overkill if we're only interested in its expected value, because then we can work with the PDF or CDF of x rather than the CDF or PDF of g of x. Okay, so the expected value of a function of a random variable is defined as follows. Okay, and the difference now is that instead of putting in u, which multiplies the PDF, is now g of u, so the function of the random variable. Okay. Otherwise, we see here now that we still have the PDF of x, not the PDF of g of x. Okay. So this is very, very convenient. So we use this often. And one specific function of g would be the squaring function. So the expected value of x squared, by just instead of g here putting the squaring function, we get this. So u squared. So g is the squaring function, so u squared here. And this is the integral that we need to calculate. This expectation has a specific name. It's called the second moment of x. Then the third moment is when we have the 3, and the fourth moment when we have 4. We would not deal with this. We would just work with the first and second moment. The first moment is actually the expected value, x raised to 0, x raised to 1, sorry. Okay, the variance of x is the expected value of x where we subtract off the expected value of x squared. Okay, so let's take that again. So we take a random variable and we subtract off its average, and then we get a random variable which has expected value 0 actually. Okay, and then if we square that, that is the variance of x. And by definition, by just looking at this function here, it's u minus e to the e of x here. This is just a number, right? So the function here of x is, instead of x, we put in u here, and this is just a constant, so we subtract that off, and then was a squaring function. So this is by definition the variance, or the expected value of what's inside the brackets here. And this is known as the variance. So the variance tells us how likely we are to be away from the average. If the variance is large, then there is a lot of variations around the average. If the variance is very small, then there is not a lot of variation around the average. Okay, so the square root of the variance is known as the standard deviation, right? So that's something which is also used for this purpose. All right, and then one property of expectations which is super useful is that it's linear. So the expected value of some linear combination of x, so some scaling of x and adding constants to this, is that we can break out the constant values here. So we can break out, first of all, the expected value. So we have a linearity here. So essentially, if we want to do this in 2 steps, the first thing to do is that through the linearity, we can write this as a times x plus e of b. The expected value of a constant, a non-random quantity, is the quantity itself. Okay, so this is always b, regardless of what the value of b is, because b is not random here. Then we can continue and use linearity on the first term, and then we can write this as e, the expected value of x, plus b. And the expected value of, so that's what it is. It's the expected value here, and we can pull out, and we can pull out a here. So then we get this formula. Okay, and this is very simply proven by just taking the generic formula for the expectation of a function of a generic formula for the for a function of x, and just plug it into this formula here, and we use the linearity properties of the Riemann integral, and everything falls out like this. Okay, questions? Okay, now for discrete random variables, we can do exactly the same thing, but instead of integrals here, we have sums. Okay. Statistical independence. So this is something which is very, very important and also very difficult to deal with. In the sense that how can we say that two... okay, so let me explain what it is in mathematical terms, and then we take the interpretation later on. It is when we have two random variables, x and y here. So think of x as being the temperature in this room, and y is the temperature on Hawaii. Okay, so just to take two random things here. We say that these are statistically independent if the joint CDF of x and y, which by definition is the probability of this event, the probability that x is less than u and that y is less than w, so less than v. Okay. So this means and. Okay, so the comma is and. So the probability of which event are we looking at? We have probability of the event that both x is less than u and y is less than v. Okay, so the probability of these events is something, but if x and y are statistically independent, then we can write that as the product of the two probabilities. Okay, so this is true if we have independence. It is not true if we don't have independence. Okay. So when x here, okay, which is then, if we then just take it one step further, we see it's the product of the CDFs here, by definition. Okay. So when can we say that two things are independent? Well, usually this is by assumption. We just assume that they are not related to each other. Sometimes we can also prove that they are not related to each other. But when we start like saying, so say that x is the temperature in this room and y is the temperature on the main island of Hawaii, for instance. Can we think of these as being independent or not? What do you think? Are they independent? Probably, right? Okay. There are so many things that happens between this room and Hawaii that if I knew the temperature in Hawaii, it would not tell me much about what the temperature is here, or vice versa. So this is by assumption something which is independent of each other. And then we can do this. Okay. Now the temperature in this room and the temperature in the corridor, are these independent? Probably not, right? Because we share the same air conditioning. There's no Well, maybe there is air conditioning here, I don't know. But we share the same heating system. There is some leakage through the walls and so forth. So if I knew the temperature in the corridor, I can say something about the temperature inside here with some, not with complete accuracy, but with some certainty, right? So if it's 20 degrees outside in the corridor, it's likely to be around 20 degrees inside, right? It will at least not be freezing. We know that, pretty sure. Right? Could be freezing if somebody left all the windows open. We don't know, right? But anyways, so that's the flavor of independence. So independence basically tells us that we have two random things which are not related to each other, and then we can treat them separately. If they are related, then we need to treat them jointly. Okay, so anyways, if we have this independence that we can factor the joint CDF into the product of the CDFs for each of the random variables, then if we take the derivative of the left-hand side here and the derivative of the right-hand side here with respect to u and v, we see that the joint PDF of x and y is the product of the PDFs of x and y. And this holds also for both for these formulas holds both for continuous and continuous and discrete variables, except that the relationship between the CDFs and the PDF is through derivative, but that's not true for continuous random variables. Then there is no derivative. Okay, maybe I just confused you there. But anyways, this holds for both continuous and discrete random variables from the notation that we have introduced. Question? Thank you. It's a break, so let's take a break.